Perhaps you had the opportunity to play, or at least heard about, the 20 questions game. It's a classic guessing game where one person secretly thinks of an object, person, or animal, and the other players try to identify it by asking up to 20 yes or no questions. A typical set of questions might start with whether it's a living thing. If yes, then whether it's an animal. If it is usually kept as a pet and it barks, it's a dog. But if it doesn't bark and instead meows, it's a cat. The quality of the questions asked determines how quickly we can guess correctly, and this is crucial in this game. It turns out that the art of asking proper questions is not only important for games, but also in everyday life. It is also the basis of the decision tree algorithm, one of the most popular methods for decision making and classification. To learn more about this algorithm, let's start with an everyday example. What to wear when going outside? To choose the proper outfit, we can first check if it's warm. If yes, we still have two options left, so we must keep asking. If it's not a formal occasion, we could go for a casual t-shirt, but if it's formal, we put on a collared shirt. If it's cold and formal, a suit jacket is fine, but if it's cold and informal, we can ask ourselves whether we prefer simple or patterned clothes today and decide accordingly. In this way, we created our first full decision tree-like structure that, as its name suggests, is intended to make decisions, answer questions, and classify data samples by simply asking yes-no questions, starting from the top and splitting step by step until we reach an answer. Each decision tree is made of the same components, nodes and branches. The first node is the root node. The following questions are internal nodes, and the terminal nodes are leaf nodes. All nodes are connected by branches. So, we deal with tree-like terminology here, but the chart still doesn't really resemble a tree. Only when we add color and turn it upside down, we see why we have the root at the base, then branches and leaves, and why it is called a decision tree. But for reasons like convention and natural reading direction, we usually stick to this upside down form. In practice, among many applications of this method, some of the most popular are medical diagnosis and marketing product recommendations. Interestingly, we can even use a decision tree for chess-related tasks, such as predicting how many moves remain in the final stage of the game. Let's now focus on the medical case. We will try to determine whether a patient is likely to have diabetes using the Pima Indians Diabetes database. This dataset consists of 768 female patients, all aged 21 and older, of Pima Indian heritage from Arizona, USA. Some of them were diagnosed as diabetic and some as non-diabetic. For each patient, 8 numerical features are provided: age, number of pregnancies, body mass index (BMI), and some basic test results like blood pressure, glucose, etc. The last feature, diabetes pedigree, represents family history of diabetes turned into a number. What we want to achieve here is to use this dataset based on past experience to diagnose new patients and decide whether they are likely to be diabetic or not. Just like a doctor is able to diagnose patients based on experience and also provide an explanation for the decision, maybe because of high glucose, high BMI, or another reason, We expect the algorithm to do the same. We could use neural networks, for example, train them on our dataset and get predictions. But what this algorithm lacks, or makes very hard to obtain, is the explanation for its decision. We won't really know why the neural network decided what it did. Such models are called black boxes, because we get a result without explicit explanation. What we really need here is a white box model that provides both the result and the explanation, just like a doctor. So let's check with this medical example whether decision trees can give us both kinds of information. We already know what a decision tree looks like from the previous example, and using this knowledge and our dataset, we can try to answer whether a patient is diabetic or not using another decision tree. Maybe this one. With a new patient, to make a diagnosis, we collect the necessary information, answer questions about glucose and other parameters, and predict a diagnosis. This is how it works. Once we have the decision tree ready, where each path ends with a leaf node, we can use it whenever we need. But there is one issue here that makes this tree impractical. All these questions are just my proposal and have nothing to do with the real-world data from our dataset. So, how can we choose proper questions? Let's start with the first split at the top of the tree. Out of 8 features, which one should we select first? Should it be glucose, BMI, or maybe insulin? And if insulin, what threshold should we set? To answer this, let's change the way we display our dataset. We have 500 non-diabetic and 268 diabetic patients. I will present these numbers and classes as a blue and red horizontal strip with proportions corresponding to class sizes. Now, let's define what we want. Ideally, we would ask a question that perfectly splits patients into two groups, non-diabetic and diabetic. That would be the perfect question, and we would be done. But as you may suspect, life isn't that perfect, and such situations are extremely rare. So, let's first try with a skin thickness and maybe glucose. Which one is a better question? Which one makes a better split? We see that neither is perfect, and patients from both classes are mixed in both yes and no answers. Let's compare these two with our perfect imaginary question and check which is closer to our goal. On the left, we see definitely more blue in the second question than in the first, making it closer to our perfect blue strip. On the right, the bottom class distribution resembles the perfect red strip more than the top one. So, maybe the glucose-related question is better. Even if it is, we still have other features and thresholds to compare, so a lot of work remains. What we really need is a single number for each question, each split, that tells us its quality. The bigger, the better. Then we could simply choose the question with the highest quality. It turns out that entropy is one possible function that we can use. Entropy measures the disorder of a dataset. It's lowest when all samples belong to one class, and highest when classes are evenly mixed. Imagine a bowl of candies. If they're all the same flavor, you don't need to check which one you pick, so entropy is low. But if every flavor is mixed equally and you want to get your favorite, you must look carefully, so entropy is high. Here is the formula for entropy, but what matters now is how it works in practice. At both edges of the plot, where our distribution strip, this time vertical, has only one class, entropy is 0. Exactly in the middle, where disorder is highest, entropy is 1. Anywhere else, for two classes, the value is between 0 and 1. The closer to a single class, the closer to 0. At the beginning of tree creation, we usually start in a high entropy area, and we want our distributions after the split to move closer to the edges, into low entropy areas. Let's take our perfect question as an example. With the original dataset, we start here, and after the split, one distribution moves to the left edge and the other to the right edge. Before, entropy was here, but after the split, entropy is 0 for both sides. We cannot go any further. Entropy is minimal, and this is why this question is perfect. How about the skin thickness question? We start as before, but the proportions after the split look exactly the same as the original dataset before the split. So we end up in the same place. Entropy before and after is the same, so there is no drop in entropy. Let's check the second question. We made progress. We pushed the two new strips a little outward. We already know the entropy before the split, but what if the entropies after the split differ? Should the combined after entropy be lower, higher, or in between? The solution is weighted entropy. So first we read the entropy before from the plot, and it's 0.93. After the split, one branch has entropy 0.67 and the other 0.99. To compute weighted entropy, we consider the size of each branch relative to the original dataset. The larger the branch, the bigger its influence. Summing the two entropies, each multiplied by its share, we get 0.82. That is our entropy after. Now, we can compute the drop in entropy, called information gain. And that's the quality measure we need. Information gain is simply entropy before minus entropy after. The reduction caused by the question. In our case, for glucose less or equal to 120, the information gain is 0.11. And how about the skin thickness question? Entropy before and both entropies after are the same, 0.93. So the weighted entropy after is also 0.93, giving information gain 0. This question adds no useful information. Now we finally have a single quality number for each split that tells us how good it is for decision making. Next, we must check all features for the best split, and for each feature, try all possible thresholds. For example, for age, we start with the lowest threshold, compute information gain, then move to the next and continue up to the maximum. When finished, the bottom plot shows information gain versus the age threshold. The brighter area, the higher the gain. Let's compare splits for the highest gain at age 28, then 36, smaller gain, and 45, even smaller one. On the left, the class ratios for these three distributions are similar. The main difference is the number of elements. On the right, the blue to red ratio is largest around age 28 over 4:1, making it the best split for age, even with a fairly large left side branch. Now look at the other features. The highest information gain values appear for glucose, especially between 100 and 170. Age and BMI also show high values. The single biggest value is at glucose equal to 127. Because it maximizes information gain, that should be our first question. After splitting, one group moves strongly toward the red class, the other toward the blue. That's exactly what we want. What next after the first split? We move down to each resulting distribution and treat it as the new dataset to split. Again, we search for the best question based on the current distribution. Here, it will be BMI less than or equal to 30, and then proceed to the next branch at the same level. We continue downward and repeat. We can keep splitting, but sometimes it's worth stopping at a chosen depth. If we split too much, the tree starts overfitting, memorizing small details instead of capturing the bigger picture. Even if a branch isn't pure, only one class, we can still decide by majority class. Take the first left side branch. It has a strong majority of diabetic cases and only a few non-diabetic, so we assign diabetic at the leaf. This means we introduce some errors during tree construction, and misclassification may occur later. It's good to be aware of this when analyzing results. Returning to the tree, we can do the same for the right side strip. That one is clearly blue, so non-diabetic. And we can do the same similarly for other leaves. And what insights can we learn? On the right path, patients with glucose less than or equal to 127, age less than or equal to 28, and reasonably low BMI are mostly non-diabetic. On the left, high glucose, high BMI, and then even higher glucose levels lead to a diabetes diagnosis for most patients in that group. An interesting case is that sometimes a question doesn't matter. Regardless of yes or no, we classify it as a diabetic. Then it's a good idea to remove that question and classify based on the previous one. We can do the same with two other nodes. Removing parts that don't add much new information is like trimming real trees when they grow too large, and it has the same name, pruning. Once we have finished growing the decision tree, we can diagnose new patients by following the questions. If a patient has high glucose and BMI over 30, she is likely diabetic. We can also state it in explanation form. High glucose and high BMI contributed to the diagnosis. That's exactly what we wanted, a result with an explanation, which makes a decision tree a white box model. The entropy-based decision tree I presented was introduced and first used in 1979 by Ross Quinlan. This was around the start of the personal computer era and 3 years before the first commercial CDs. Decision trees are widely used because they are simple, intuitive, and easy to explain visually, even to non-experts. Moreover, they can use both numerical and categorical features and require minimal processing, if any. On the other hand, they are prone to overfitting, and small data changes can produce very different trees, making them less stable. These issues can be mitigated within decision trees, like using pruning or depth limits, or with ensembles such as random forest, But that's a story for another video. Thank you for watching.